Xendee provides a variety of options to achieve voltage regulation objectives, and one of the OpenDSS features Xendee makes available is the modeling of line voltage regulators, which are sometimes referred to as line drop compensators. These devices provide feeder regulation, and each feeder is individually regulated by a single-phase step voltage regulator. Beckwith Electric has a wonderful guide on voltage regulation, and as they explain, the main feature of modeling a line voltage regulator versus, say, just an LTC is the impedance of the distribution feeder, which is needed in order to properly compensate for the voltage drop caused by a long wire run to a load. The challenge, which they discuss, is that there are seldom clear real-world situations where a single long wire is the only load off of a feeder. But regardless, let's take a look at how you would go about modeling a line voltage regulator. Let's assume for this example that we wish to control voltage at the load off of wire 7. There are a few data points we need to have available. A regulator is modeled similar to a standard two-winding transformer, but with some additional settings. First, you will need to provide the regulator voltage, which Xendee defaults to 120 volts. This is the voltage used by the control and is achieved in the field by installing a voltage transformer which converts the bus voltage to 120 volt AC basis. Next, you will need to provide a bandwidth, and we provide a default of 3 volts. This input is needed in order to provide some range of voltage around the desired voltage you wish to hold at, in this case 240 volts. This allows for some variability due to the step change nature of the LTC output, and any value within this range will then be considered in band. Again, this value is expressed in volts based on the 120 volt base, and 1/2 of the range is allowed above and 1/2 below the desired voltage level settings. You will need to provide the PT ratio, which Xendee provides a default for, but if you wish to change the regulator voltage to something else, such as 125, you can either manually enter a different PT ratio or click on the calculator button to have one automatically calculated for you. You can also enter in a time delay. Although the snapshot power flow does not use this feature, dynamic power flow will. This is an intentional delay that is typically programmed into the line voltage regulator settings in order to avoid tap changer operations when the voltage exclusion outside of that bandwidth that you've defined is of short duration. Xendee defaults to 15 seconds, but you can change it to some other typical values such as 30 or 60 seconds. You will also need to provide the CT rating in amps. This value is a rating for converting the line amps to control amps. And as mentioned earlier, the control needs to know the values of resistive and reactive voltage drop for the line when the line is carrying the primary rated current of the CT. These RNX values are calibrated on the control in volts and not ohms. Beckwith Electric has a nice document on how to estimate these values, and most controls have a range for R and X between -24 and +24 volts. Once these settings have been defined, we can simulate a network and see the voltage regulation impact. So let's go ahead and perform a snapshot power flow on this sample network to see voltage control along with the calculated tap position of the line voltage regulator for our voltage control objective of maintaining 240 volts at the load. You'll see that tap position has been calculated and voltage at our load is now within the bandwidth setting. This concludes our brief tutorial on line voltage regulators.